Okay, so we'll be moving on to section 4.4, and we're going to be talking about absolute maxima and absolute minima. So we have a definition. So consider an interval in the domain of a function f and a point x naught in that interval. We say that f has an absolute maximum at x naught if f of x is less than or equal to f of x naught for all x in the interval. And we say that f has an absolute minimum at x naught if f of x is less than or equal to f of x, if f of x naught is less than or equal to f of x for all x in the interval. And we say that f has an absolute extremum at x naught if it has either an absolute maximum or an absolute minimum at that point. So it's fairly intuitive. Absolute maximum, we're looking at the highest point in the interval. Absolute minimum, we're looking at the lowest point in the interval. So maybe we have a graph that looks like this. And so it goes up, comes back down, goes back up. And we're only looking at this part of the graph, right? So you have a relative max here, because this point is higher than its immediate neighbors, but you have this point over here that's higher than it. So that point is absolute max. Be careful, this is not a relative max because we can't draw a little interval in the x-axis and put numbers in. So the endpoints are not considered relative extrema, but they can be absolute extrema. We do have an absolute minimum down here. This point is lower than its immediate neighbors. And so we're going to want to find it. Okay. So we're looking for these things. Now, if you think about it, we've talked about polynomial functions. And in polynomial functions, if your one possibility is that your function takes off to negative infinity on the left and off to positive infinity on the right, and who knows what it does in the middle, but somehow it'll connect. And here you can see from the picture that you don't have an absolute max or an absolute min. The graph continues forever in this direction and in this direction, so you don't have an absolute max or an absolute min. Turns out, though, that if this theorem here tells us that if a function f is continuous on a finite closed interval, ab, then f has both an absolute maximum and an absolute minimum on that interval. So if you're only looking at part of this graph, and we cut off that section, and we cut off that section, now you're guaranteed both an absolute max at the endpoint and an absolute min at this point here in the middle, right? So it's fairly intuitive. The proof is beyond the scope of this class, but it seems reasonable. Moving on, we're on to the next theorem that says if f has an absolute extremum on an open interval AB, then it must occur at a critical point of f. So if you look at that last example that I drew, our absolute maximum was at an endpoint, but this theorem is talking about being inside the interval, not at the endpoints. And our absolute minimum was down here. And so that one is at a critical point. That should make sense. It should make sense because if you have a relative extremum, then it's going to be, if you have a absolute extremum in the interval, then it's going to be a relative extrema. And what we saw last section is that the relative extrema happen at the critical points. And so that's fairly easy. And so we'll practice here with this problem. It says use the graph to find the x-coordinates of the relative extrema and absolute extrema of f on the interval from 0 to 7. So we're only interested in this graph, and really we should have endpoints here telling us that this is where the graph ends. There's no part of the graph beyond that. So relative, we need to be able to draw a little interval in the on our graph, and so we can only do that on the inside. Here at 1, and at 3, and at 5, and that's it. So at 1, we see that we have a relative min, and then it's only asking use the graph to find the x coordinates. So at x equals 1, and then again 2, 3, 4, 5, and then at 5. Relative max, we have one here at 1, 2, 3, at 3. Now, we do have a continuous function. You can see that it's all one piece. It is on a closed interval, on the interval from 0 to 7, so the theorem guarantees us that we have to have an absolute max and an absolute minimum. The highest point on the graph is where your absolute max is, and so we have the absolute max at x equals 7. The program continues to fill in lines where I'm not asking it to. Don't know how to fix that. And then we have an absolute min at x equals 1 and at 5. Both of them have the same y value. Okay, let's move on. Now let's do this analytically, right? So find the absolute maximum and minimum values of f on the given closed interval and state where those values occur. So you're looking at a polynomial function over this closed interval from -3 to 2, including the -3 and including the 2. And so then the theorem guarantees us that we have an absolute maximum and an absolute minimum. The second theorem says if it happens on the inside, it has to be at a critical point. But as we saw in the last example, it could happen at the endpoints. So then what you would need to remember is that when you have a continuous function on a closed interval, you're guaranteed an absolute max and an absolute min, but you have to look at the endpoints and the critical points. You won't need the first derivative test or the second derivative test. What you're going to do is you're going to find the first derivative, 6x squared plus 6x minus 12. You're going to look for the critical points, and no need to set it equal to 0. You can just write your function in factored form. And so we can factor out the 6, leaving behind x squared plus x minus 2. And then we can factor that x plus 2, x minus 1. And so then 2x and minus x make us plus x, so we're good there. So our critical points are at -2 and 1, and my endpoints are at -3 and 2, and we want to know what is the biggest output for this function, not for the derivative. So you have a couple functions here. You're trying to find the absolute max for this function, so be careful with that. Don't substitute into your derivative. We make a table, f of x, and on this table, the only numbers that we're going to put in are our endpoints, -3 and 2, and our critical points. And we can tell from the derivative that these will be -2 and 1. Now, the quickest way to do this is to take out your calculator, go to your y equals, and put in your original function, 2x cubed plus 3x squared minus 12x. Now you should practice this as well because you need to be able to use your calculator. And then you go to your table set and make sure that it's on ask. And you put in -3 and the calculator tells me 9. You put in 2, the calculator tells me 4. And you put in -2, the calculator tells me 20. And then you put in 1 and the calculator tells me -7. Okay, you can see then your highest output, your biggest output is right here. This corresponds to your absolute max. And then your lowest output is this one over here, at -7. And so that is your absolute min. In this case, both your absolute max and your absolute min happen at your critical points, not at the endpoints. Now, what you can do with this, and once you put this in your calculator, you can check your calculus and make sure that it's right by looking at the graph, right? So we can go to our window and just set the window to go from -3 to 9. And we can set the scale at 1, that's fine. But the y-min needs to go from a minimum value of -7 to a maximum value of +20. We need a scale of at least 2, so I'll do 3 since 27 is easily divisible by 3. And then when I look at the graph, if the graph doesn't fit in that interval, I have done something wrong. So when I look at my graph, it fits perfectly in that window, right? And the graph I am seeing looks like this. Right? And so you see your relative max is over here. It happens at an x coordinate of -2 and a y coordinate of 20. Your relative min, I'm sorry, not relative, your absolute max is at -220, and your absolute min is at 1, -7. Okay, let's move on. And again, it's probably really boring to sit here and watch this for an hour at a time. So one of the things you can do is pause it, go do some homework, pause it, and try the next problem on your own so that you can match your work and my work. Okay, so you can do that now. So I'll continue with the problem. So we're doing the same instructions. So we need to find the critical points and the endpoints. And so we have to take the derivative. This is a composition, so if we bring down the exponent, take 1 away from the exponent, so 2/3 minus 1 is -1/3. Same inside. Times the derivative of the inside. Okay, so notice that my function is continuous, and because it is just a power function, and so we have a composition of a polynomial function and a power function, so this is continuous. To make my sign chart, I can make it from here, right? So the only thing that is going to make this 0 is oh, I'm sorry. Let me step back a moment. So we can't make it from there. It'll be a little easier if we go ahead and rewrite this. The 2x plus 1 stays in the numerator. The -1/3 goes into the denominator. The -1/3 becomes x times x plus 1 to the 1/3. And then now in factored form like that, we can tell what are the critical numbers. What are the numbers that make the derivative 0 or undefined? So to make it 0, we need to make this 2x plus 1 0, which will be -1/2. To make it undefined, we use 0. And then to make this 0, we need -1. So everything here is happening in between -1, -1/2, and 0. Okay. Okay, so I got sidetracked a little bit. I'm sorry. Um, we don't need to make the sign chart. We know that we're trying to find the absolute maximum and absolute minimum of this function, and all we need to know are what are the critical points, right? And so once we write it like this, we can see that the critical points are the numbers that make the derivative 0, negative 1/2, 0, and negative 1. We also need the endpoints, and the endpoints are negative 2 and 3. Make sure that all of your critical points fall in the interval from negative 2 to 3, and in this case they do. And again, x, f of x. And again, what we want to do is we want to go to y equals and put this in. And we have x squared parentheses x squared plus x raised to the 2/3. We want to put in negative 1/2. And that will give me 0.3 0.39685. And then we want to put in 0, but when we put in 0, we can do that without the calculator. We're going to get 0. When we put in negative 1, that's also going to give me 0. And then when we put in negative 2, that'll give me 1.5874. And when we put in 3, that'll give me 5.2415. So this is my absolute max. And that happens at the endpoints. This is my absolute min. And this is also my absolute min. And that happens at 0 and negative 1 at the critical points. At negative 1/2, we don't have an absolute max or an absolute min. We could have a relative min, but we're not interested in finding the relative extrema in this. So we can go to our window, set our window to x values between negative 2 and 3, and an x scale of 1, and y values between 0 and 6. When we look at the graph, we see that at negative 1/2, we did have a relative extrema. We weren't interested in that. And what my graph looks like when I look at this is it looks like this. Comes down. We have a cusp right there. Goes up. And then it takes off like this. And so then there is our relative minima right here and here. And we have our absolute max over here at the endpoint. Sorry, not relative. This is absolute minima. Okay. We'll now do a little trig. Find the absolute maximum and absolute minimum values of f on the given closed interval and state where those values occur. Again, we're just looking for the absolute max and the absolute min. We don't need the relative max and relative min. So we don't need sign charts, right? We just need to find the derivative, find the critical points, make a table. So let's go on to do that. So find the derivative. F prime of x is equal to the cosine of x plus the sine of x. Find the zeros of this in the interval from 0 to pi. So can't do that by inspection. So I set that equal to 0. And we saw this on our last section. When we see something like this, we can try and get the tangent function in here by subtracting the cosine of x from both sides. Dividing both sides by the cosine of x. we'll then make this the tangent of x. Only one trig function. And over here we'll get -1. Okay, so again, we're only, be mindful of the interval. We're only interested in this in the interval from 0 to pi. And the tangent is -1 in quadrants 1 and 4. But in quadrants 4, can't get there with an angle from 0 to pi. So we're not looking at that one. Okay, so tangent to be -1 means that my reference angle is pi over 4. And so then x needs to equal 3 pi over 4. So then there's only one critical number, only one place where this derivative is 0 in the interval from 0 to pi. And so then we make our table. And on our table, we put our endpoints, 0 and pi, and our critical points, 3 pi over 4. Sine of 0 is 0, cosine of 0 is 1, so at 0 we get -1. Sine of pi is 0, cosine of pi is -1, so 0 minus -1 is +1. And 3 pi over 4, sine of 3 pi over 4 is the square root of 2 over 2. Cosine of 3 pi over 4 is negative the square root of 2 over 2. And so those now become 2 square roots of 2 over 2, or just the square root of 2. Okay, so you can see that this is your absolute max, and this is your absolute min. Again, take a quick look at the graph, just to make sure that what we're saying matches up. We want the sine of x minus the cosine of x. We're only interested in the interval from 0 to pi. My scale, I'll make it pi over 4 so that it looks a little prettier. And then my y min, -1, and my y max, 1. I'm sorry, the square root of 2. My scale, I'll make it at 1. And the graph that I am getting from 0 to pi goes up here and then comes down. That's at pi. And this is at 3 pi over 4. So it gets this maximum value. And then over here you get your minimum value. Matches the table. Matches my critical point. This is the only critical point. There is no other critical point. So everything looks good. Let's move on. So now we're going to look at absolute extrema on infinite intervals, some possibilities. As we said, your polynomial functions take off to positive or negative infinity as you go off to positive or negative infinity. And so those aren't guaranteed to have an absolute max or an absolute min. But if on the endpoints, both times you're taking off to positive infinity, both on the left and on the right, then if you're continuous, you have to have a absolute min. Likewise, if on the ends you're taking off to negative infinity and negative infinity, then somewhere in the middle you have to have a high spot, an absolute max, right? But if you're taking off both to negative infinity and positive infinity, as in these last two, you don't have to have an absolute max. You don't have an absolute max or an absolute min, right? So again, I encourage you to try the problem, pause it, see if you can do the problem on your own, and even if you can't, you'll know where you get stuck, right? So in 21 through 28, find the absolute maximum and minimum values of f, if any, on the given interval, and state where those values occur. right? So we see that it is even degree, so x to the fourth, and on top of that, the leading coefficient is positive, so you know that on the ends, it's going to go off to positive infinity and positive infinity, whether you are looking at the right or the left. But what we want to do now is figure out what is the absolute min. So we know there's no absolute max, but we know it has an absolute min. Makes sense that if it's going to have a absolute min, it'll be a relative min. So we find all the relative min and see which one's the lowest one. So f prime of x is equal to 4x cubed plus 4. We're looking for the critical numbers to find the relative extrema. Factor out the 4, and you get x cubed plus 1. This is the sum of two cubes, so we can continue our factoring work because this is going to be x plus 1 times x squared plus x plus 1. And then the critical numbers are whatever makes this 0, which is -1. And if you use the discriminant, you'll find that nothing makes this 0. So your only critical number is at -1. So you only have one relative min. And so that has to be your absolute min. So then absolute min at x equals -1. Find the absolute maximum and absolute minimum values. That's asking for the y values, and so we can figure out the y value by finding f of -1. And when you put in -1, you get 1 minus 4, which is -3, and this is your absolute min. Okay. Moving on. Find the absolute maximum and absolute minimum values of f, if any, on the given interval, and state where those values occur. Okay, so again, the monomial of highest degree in this problem is this x cubed. You should know what x cubed does on the ends. X cubed, because it's odd and the coefficient is positive, it takes off to positive infinity on the right and negative infinity on the left. Since we're looking for just the absolute min, this is the work that you show. You draw this little sketch right here, and you say no absolute extremum, right? Because there is no lowest point, since over here it takes off to negative infinity, and over here it takes off. There's no highest point, since over here it takes off to positive infinity. Okay, got another toy. Need my pen back. So find the absolute maximum and minimum values of f, if any, on the given interval. So notice that we are not guaranteed a absolute max and min because our interval here is open. It is not a closed interval. So since it is continuous on this interval, so we're not guaranteed that. But let's see what the derivative tells us. Okay, so my first derivative is f prime of x is equal to, the derivative of the secant is the secant of x tangent of x. So 5 times the secant of x times the tangent of x. And so then we're only looking in the interval from pi over 2 to 3 pi over 2. Pi over 2 goes from here to here. 3 pi over 2 goes from here to here. So we're only looking at angles that fall in here, right? And the secant is undefined at pi over 2 and 3 pi over 2 because the secant is 1 over the cosine. But the tangent at pi over 2 is fine. It's I'm sorry, it's undefined as well. But at pi, the tangent is 0. So there's no numbers that make the derivative undefined in this interval, and the only number that makes it 0 is pi. So we only have one critical number, right? Now, if you're not familiar with what x equals pi is the only critical number. If you're not familiar with what the graph of the secant looks like, then you may not know what we have here. So what we might want to do is look at the sign chart only in the interval from pi over 2 to 3 pi over 2, which means my angles are going to be in either quadrant 3 or 4, right? And so let's go ahead and make our sign chart. And we're making a sign chart for f prime. And so our only critical number, we're only looking in the interval from pi over 2 to 3 pi over 2. And we have one critical number right in the middle at pi. But ASTC in quadrant 2, the only positive function is the sine, so both the cosine and the tangent are negative, and so then when you multiply them together, the secant and the tangent, you're going to get a positive. And once you get past pi, then your only critical number, then once you get past pi, you're over here in quadrant 3, and so there the tangent is positive and the cosine is negative, so you are negative. So that tells you that to the right of pi over 2, your function was going up, and then it started going down. So you have a relative minimum, right? But since in this entire interval you were going up and then down, that should make sense then that not only is that your relative minimum, it's also your absolute minimum. So here, because we only have one relative extrema, it turns out to be the also the absolute extrema. And so that's going to, so then we have an absolute max at x equals pi. And if we were to look at the graph of that, again, like I said, at pi over 2 and 3 pi over 2, the cosine is 0, so the secant is undefined, and we have a vertical asymptote. Right in the middle at pi, the cosine of pi is -1. The reciprocal, the secant, is also -1 times 5 is -5. And then since you have a vertical asymptote, your graph must have been going like that. And so you were climbing, and then turning around. Since there was only one spot at which you did that, since you only had one relative extrema, that has to be your absolute extrema. And your absolute max is -5. That leads us to our next theorem. It's going to be useful from time to time. So suppose that f is continuous and has exactly one relative extremum on an interval, say at x naught. If f has a relative minimum at x naught, then f of x naught is the absolute minimum of f on the interval. If f has a relative maximum at x naught, then f of x naught is the absolute maximum of f on the interval. So as we saw in that last example, I'm not going to prove it, just it should be intuitive that if you only have one relative extrema, then you had to have changed directions. You were either going up and then started coming down, or you were coming down and then going up. And if there's only one, then that has to be your absolute as well. Even if your interval is infinite, or if you're not a closed interval. Okay. So find the absolute maximum and minimum values of f, if any, on the interval and state where those values occur. Okay, so several ways to approach this problem, right? We're going to approach it trying to use the last uh, uh, theorem, right? And so then we have this infinite interval, but we're going to look at the first derivative, bring down the exponent, and we'll get 64 x cubed minus 96 x squared plus 48 x minus 8, and the 12 goes away. So to find the critical numbers, we have to figure out what makes this 0. Maybe we can take out an 8 to make our problem a little bit more manageable. So then here we will get 8x cubed minus 12x squared plus 6 times 8 is 48, 6x minus 1. And now you could try factoring by grouping, but it's not going to work. And so then how do we find the zeros of this? What you learned in pre-calc is that if you're going to have a rational zero, then it has to be a fraction that looks like a factor of 1, which there's only 1, over a factor of 8. So the factors of 8 are 1, 2, 4, and 8. So we should look for nice rational numbers that make this 0. And so there's not that many. It's plus or minus 1, plus or minus a half, plus or minus a fourth, and plus or minus an eighth. Those are the only possible rational numbers that will make this expression 0. But rather than going and plugging those in by hand, what we can do is go to our calculator and put in 8x cubed minus 12x squared plus 6x minus 1. Notice that our zeros have to be in between -1 and 1. So for my window, I'm just going to pick between -2 and 2. And then I'll go from -10 to 10 for the y's, and then I'll look at my graph. And when I look at my graph, just punch that into the calculator. What the graph looks like is it looks like this. And it looks like it's going right through the origin at 1/2, because this over here is 1. Okay, so I can hit the trace button, put in a half, and it tells me that it's 0. And it tells you more than that. It tells you that there is only one critical number. It's at a half. And so then since you only have one, it has to be, you only have one relative extrema. If it's a relative min, it'll be an absolute min. And if it's a relative max, it'll be an absolute max. There's a couple ways to know that it's a relative min, not a relative max. It has to be both. But because of the 16x to the fourth, we know that it can't have an absolute max, right? The other thing that we can do is we have the graph right there. We can make the sign chart for the first derivative based off of this graph. To the left of 1/2, your outputs are negative. To the right of 1/2, your outputs are positive. And so that tells you that you were going down and then going up. Therefore, you have a relative min. But since you only have one, it's also an absolute min. And then we're done. Find the absolute maximum and minimum values of f, if any, on the interval and state where those values occur. Okay, so again, we're not guaranteed an absolute max and an absolute min because we're not on a closed interval. And so if you, but we can see if it has any relative extrema by finding the critical numbers. So we find the first derivative. Okay, so it's going to be better to, rather than using the quotient rule on this, I'm going to look at this as x squared minus 2x minus 8 to the negative 1. So I will bring down the exponent, x squared minus 2x minus 8. Take 1 away from the exponent, negative 2, times the derivative of the inside. And so then the derivative of the inside is 2x minus 2. From this, you can see that what's going to make it undefined is what makes this 0. What makes this 0? But we already know what makes that. If we plug in negative 2, so we'll get 0, and if we plug in 4, we'll get 0. To see that, you can just write that in factored form. X minus 4, x plus 2 to the negative 2. Here you can factor out 2, or you can see just by inspection that 1 will make that 0. So negative 2 and 4 are not in your interval because it's not including negative 2 and 4. Negative 2 and 4 are the same numbers here, and they will make the denominator 0 in the original function. So that's why we did not include them, because they were not in our domain. And so our only critical number that's in the domain is 1. So that means this has only one critical number. But it's still not obvious whether this is a relative max or a relative min. And in factored form, we can do this by looking at the first derivative test. And we're only interested in what's happening around 1. To the left of 1, we don't have to worry about any of this right here because all of this right here is being raised to the negative 2, and that 2 is going to square it. So just to the left of 1, this will be negative, but times this will be positive. So so we will get a positive. To the right of 1, this one will be positive, but then we multiply it times this negative 1 and we will be negative. So therefore we have a relative max. And since there is only one, therefore it's an absolute max. Again, we're going up and then we're coming down, so that's a absolute max. A relative max, which then makes it an absolute max. We're done with this section. So your homework is 1 through 39 odd, section 4.4.